In the boundless emptiness that once filled the early universe, when the cosmos had barely begun to take shape, something impossible was glowing. Nearly 300 million years after the Big Bang unleashed existence itself, enormous spheres of hydrogen shimmered against the cosmic darkness. They were far too early, far too bright, and far too large to belong to that primitive era. According to every established model of cosmic evolution, there should have been nothing but cold, featureless night stretching endlessly across expanding space. Yet there it was, light where only darkness was expected. NASA's James Webb Space Telescope, the most powerful observatory ever placed beyond Earth's atmosphere, had caught these forbidden glimmers at the edge of time. The images showed red specks scattered like embers in the void, each representing a source of light so ancient that its photons had travelled more than 13 billion years to reach us. Scientists were stunned. Those tiny dots weren't supposed to exist yet. By all accounts, the first generation of stars required far more time to form. Hydrogen clouds had to cool, collapse and ignite nuclear fusion before illumination could pierce the early night. But these objects burned in defiance of that sequence, shining from an epoch when the universe should have still been a featureless sea of gas. What made the discovery extraordinary wasn't merely the distance. It was the implication that nature had found another way to shine before the first true stars were born. The data from Webb's instruments hinted at something deeply unfamiliar, something outside conventional physics. The light didn't behave as stellar radiation should. Its colour was heavily stretched toward the red end of the spectrum, a telltale sign of immense distance. But even after correcting for cosmic expansion, the brightness remained inexplicably intense. It wasn't just an observational anomaly, it was a contradiction of cosmic logic. The known process of star formation could not yet have produced these beacons. The early universe lacked the heavy elements needed for efficient cooling, without which hydrogen clouds could not condense enough to trigger nuclear burning. Yet these entities glowed with the power of entire galaxies. Every astronomer knows the universal story by heart. Darkness reigns first, gravity gathers clouds of hydrogen, pressure builds, fusion begins, and stars ignite. But this familiar progression seemed broken. The light Webb detected came from a time before fusion should have existed. To make sense of the findings, researchers combed through every possibility. Could these be small galaxies filled with unusually hot stars? Could their brightness be magnified by gravitational lensing from intervening matter? Could calibration errors or data artifacts explain away the impossible? Each hypothesis collapsed under scrutiny. The spectral fingerprints didn't match those of any known stellar population. The sources were too compact, their temperatures too low for fusion, yet their luminosity too great to be mere clusters of ordinary stars. Something unprecedented was occurring, something that required a new kind of engine. Among the scientists poring over the Webb data was Catherine Freese, a theoretical physicist from the University of Texas who had, years earlier, proposed the existence of a different class of stars powered not by fusion, but by the annihilation of dark matter itself. She had called them dark stars. For more than a decade, her idea had remained speculative, a beautiful hypothesis waiting for technology to peer deep enough into time to confirm or refute it. Now it seemed that moment had arrived. The Webb telescope had found objects that looked astonishingly like what her equations predicted. Giant, cool, puffy spheres radiating softly across the ancient void, not because atoms were fusing, but because invisible particles were colliding and annihilating within them. It was as if the universe had learned to burn darkness itself. To understand what that means, one must first grasp the scale of the observation. The light Webb captured left its source when the cosmos was less than 2% of its current age. In those days, matter was still gathering into the first gravitational wells carved by invisible dark matter halos. The universe was still learning how to make structure, and yet somehow, within those halos, luminous giants were already blazing. They were not supposed to be there, and yet they were, massive, ancient, glowing reminders that cosmic history might be far stranger than our textbooks have dared to imagine. What the telescope revealed was not simply light, but a challenge to everything we thought we knew about how the universe began to shine. The discovery forced scientists to confront an unsettling question. If these aren't ordinary stars, then what are they? Somewhere in that question lies a new chapter in the story of creation. one that begins not with nuclear fire but with the silent violence of invisible matter tearing itself apart to make the first light. When Catherine Fries first proposed the existence of dark stars, the idea was almost dismissed as fantasy, an elegant mathematical curiosity with no hope of ever being verified. Yet her conviction stemmed from a profound question that had long haunted cosmologists. If dark matter truly makes up most of the universe's mass, then surely it must have played a more active role in shaping the first structures of the cosmos than simply serving as a gravitational scaffold. Fries's insight was to imagine that in the earliest epochs, when matter was dense and interactions were frequent, dark matter could have done something remarkable. It could have ignited light. Instead of collapsing hydrogen clouds igniting through fusion, she proposed that the self-annihilation of dark matter particles could produce enough heat to prevent these primordial clumps from collapsing too quickly, allowing them to expand into massive glowing bodies. These weren't stars in the traditional sense. They were colossal spheres powered by the most mysterious ingredient in the universe. The concept seemed bold, even audacious. For years, astrophysicists had assumed dark matter was nearly inert, influencing ordinary matter only through gravity. It neither absorbed nor emitted light. But Fries's model turned that notion inside out. In her vision, dark matter didn't just hide in the cosmic shadows, it shaped the very dawn of starlight. According to her theory, when the first dense regions of the universe formed within dark matter halos, streams of invisible particles, most likely weakly interacting massive particles, or WIMPs, became trapped in the same gravitational wells as hydrogen and helium. As these halos condensed, the dark matter particles collided, annihilated one another, and released bursts of energy in the form of radiation. That radiation, instead of dispersing instantly, was absorbed by the surrounding hydrogen gas. The heat from these interactions puffed up the clouds, counterbalancing gravity and preventing collapse. What emerged was a swollen, cool, radiant object, a dark star. It emitted light not because atoms were fusing, but because dark matter was dying within it. For a long time, this concept existed only on paper, too distant and faint to test with telescopes. The first-generation dark stars would have lived 13 billion years ago, far beyond the reach of previous observatories like Hubble. No instrument before Webb could see that deep into the past. But the James Webb Space Telescope changed everything. Equipped with unprecedented infrared sensitivity, it was designed specifically to peer through cosmic time and capture the faint glow of the first galaxies. When the Webb images began returning unexpected signals, objects far brighter and larger than any early star should be, Fries and her collaborators recognized the signature instantly. These were not galaxies filled with mature stars. Their spectral patterns and temperatures aligned far more closely with what dark star simulations had predicted. In those moments, an idea once considered theoretical suddenly stood at the brink of validation. The irony was poetic. The very substance long blamed for hiding the universe's mass might have been responsible for creating its first light. The notion reframed how scientists thought about cosmic evolution. It meant that darkness itself could be a source of radiance. Fries's team refined their models, adjusting parameters to match Webb's findings. The data fit surprisingly well. The objects Webb detected seemed too large to be conventional stars and possibly spanning tens of astronomical units, rivaling the size of our solar system, yet their surface temperatures were relatively low, consistent with the cool, bloated structure predicted for dark stars. They would have glowed faintly in visible light but strongly in infrared, just as Webb observed. To the naked eye, they would have appeared as ghostly crimson orbs, floating in the vast, silent infancy of creation. Still, skepticism persisted. Many astronomers argued that these could be compact galaxies, or clusters of unusually bright early stars. But the more the data were examined, the harder it became to dismiss the dark star interpretation. The energy output, the size, the timing all seemed to align. Even the colour ratios within Webb's spectrum hinted at something other than fusion. It was as if the cosmos were whispering through ancient light, "You've been looking at the wrong kind of fire." Fries often described the theory as turning darkness into dawn. The poetic phrasing captured the paradox at its heart. If true, the existence of dark stars would mean that the universe's first luminous objects were powered by the very thing that otherwise refuses to shine. It would also mean that dark matter was more than a passive participant, it was an architect of the cosmos, capable of transforming invisible energy into visible light. Such a revelation would ripple across astrophysics, redefining how we think about the interplay between matter and energy, gravity and radiation, visibility and concealment. Dark stars were not merely an oddity, they could be the missing bridge between the Big Bang's chaos and the structured beauty of the universe we see today. Freese's hypothesis turned what was once metaphorical darkness into a literal engine of creation, a reminder that even in the most unknowable aspects of reality, there may still be light waiting to emerge. To understand how dark stars shine, one must first unlearn the conventional story of stellar fire. Ordinary stars are born when immense clouds of hydrogen and helium collapse under their own gravity, compressing until their cores grow hot and dense enough for nuclear fusion to ignite. That process, which converts hydrogen into helium, releases energy in the form of light and heat. But dark stars follow a different script entirely, one written in the invisible language of dark matter physics. Instead of relying on atomic reactions, they glow because of an even deeper form of energy release, the annihilation of dark matter particles. In Freese's model, the universe's earlier stars formed inside dense pockets of dark matter known as halos. These halos were invisible frameworks, gravitational wells made of unseen particles that pulled ordinary matter toward them like ghosts shaping clouds. When the first gas collapsed into these regions, dark matter particles, particularly WIMPs, or weakly interacting massive particles, became trapped alongside the hydrogen. Unlike protons or electrons, WIMPs don't easily collide with normal matter, but they can collide with each other, and when they do, they annihilate, releasing pure energy according to Einstein's famous equation, E mc2. It is this annihilation energy that powers the glow of dark stars. In the dense environment of a young halo, WIMP annihilation happens frequently enough to flood the surrounding gas with heat. That energy prevents the gas from collapsing further and instead inflates it outward, creating a massive, stable sphere of glowing plasma. The light emitted is softer and redder than typical starlight, because the surface temperature of a dark star is cooler, perhaps only a few thousand Kelvin compared to the tens of thousands for fusion-driven stars. Yet because of their sheer size, sometimes stretching hundreds or even thousands of times wider than the Sun, they radiate tremendous luminosity. Imagine a balloon of hydrogen and helium the size of Saturn's orbit, shining faintly in visible light but brilliantly in infrared. That is a dark star gentle on the surface, yet fueled by one of the most violent processes in nature. The physics behind this phenomenon is astonishingly delicate. If the dark matter density is too low, annihilation won't produce enough heat to sustain the star. The gas would collapse, triggering ordinary fusion instead. But if the density is just right, the annihilation energy balances gravity perfectly, maintaining the dark star's bloated equilibrium for millions of years. In those conditions, a new kind of stellar object can live and breathe, one whose heart is not atomic but cosmic. These stars represent a collaboration between the visible and the invisible, between matter we can see and the matter we cannot. Their very existence blurs the boundary between physics and mystery. They also offer an elegant solution to a long-standing puzzle about the early universe. For decades, astronomers struggled to explain how the first supermassive black holes could have formed so quickly after the Big Bang. Ordinary stars, even the most massive ones, couldn't have grown large enough to collapse into billion solar mass black holes in such a short time. But dark stars, if they existed, would change the equation entirely. Because they can keep accumulating gas while powered by dark matter annihilation, they can grow to astonishing proportions, up to 10 million times the mass of the Sun. When the supply of dark matter eventually runs out, gravity takes over, and the star collapses into a black hole far larger than any that fusion alone could produce. These collapses could seed the supermassive black holes observed in the early cosmos objects that conventional models can't fully account for. In that sense, dark stars might be the missing link between the first light and the first darkness, between creation and collapse. What makes them even more fascinating is their dual nature. They are cosmic paradoxes, born of the unseen yet radiating light, sustained by destruction yet preserving balance. Every second within a dark star, countless WIMP pairs annihilate, transforming invisible mass into visible energy, a process so efficient that even a tiny fraction of dark matter can outshine an entire cluster of ordinary stars. But the glow is deceptive. Because they are cool and diffuse, dark stars would appear as faint red smudges in visible wavelengths, barely distinguishable from galaxies, which is why only a telescope like Webb capable of capturing the stretched infrared signatures of ancient light could ever detect them. Their gentle warmth hides unimaginable violence inside, a quiet reminder that creation often arises from annihilation. In the cosmic drama, they are both actors and fuel, burning not through fusion but through the fundamental death of particles themselves. If Freese's theory is correct, then these stars are monuments to the duality of existence, matter and antimatter, seen and unseen, life and decay. Their light is the last echo of dark matter's self-destruction, illuminating the young universe in a glow that shouldn't exist, yet undeniably does. They remind us that even the most mysterious forms of matter cannot resist the urge to make themselves known, even if only through the faintest whisper of light across billions of years of space and time. For decades, dark stars existed only in the realm of theoretical speculation, a mathematical ghost story whispered among physicists who dared to imagine that darkness itself might one day burn. The idea was elegant, but elegance is not proof, and for years there was nothing to confirm or deny its reality. The universe, after all, keeps its oldest secrets buried in light so ancient that even the mightiest telescopes once failed to reach it. That changed when the James Webb Space Telescope began sending its first images back to Earth. Designed to peer deeper into time than any instrument before it, Webb could collect photons stretched across billions of years of cosmic expansion, capturing the earliest glimmers of creation itself. Among its many unexpected discoveries were strange, distant objects that seemed to defy everything astrophysicists thought they understood about the early universe. They were too bright, too large, too massive, and far too mature to belong to such a young cosmos. The light from these objects came from just a few 100 million years after the Big Bang era, when galaxies should still have been forming from diffuse hydrogen clouds. Yet these structures glowed with the intensity of billions of suns. When researchers analysed their spectra, they found something even stranger. The energy distribution didn't match that of ordinary galaxies filled with fusion-driven stars. Instead, the light carried the faint, broad signature of cooler temperatures and enormous sizes, exactly the sort of spectral fingerprint predicted for dark stars. The connection was impossible to ignore. Catherine Freese and her collaborators had long predicted that if dark stars existed, they would appear in Webb's data as super-bright, super-red objects luminous in the infrared, vast in radius, and yet lacking the sharp spectral lines characteristic of normal stellar populations. When Webb's instruments began returning data that matched this description, the astrophysical community found itself on the edge of revelation. Some of these candidates, such as the mysterious objects labelled JADES GS Z13 and JADES GS Z11, seemed to fit the dark star profile with uncanny precision. They existed so early that ordinary models of galaxy formation couldn't account for them, yet their apparent sizes and luminosities were consistent with the energy output expected from dark matter annihilation. It was as though the universe itself had written Freese's equations into the sky. The challenge, of course, was proving it. Science demands more than coincidence. It requires a spectrum, a signature, an unmistakable fingerprint of physics in motion. So astronomers began dissecting the data, comparing every possible explanation. Could these objects be compact galaxies of young, massive stars? Could gravitational lensing be magnifying distant sources into deceptive brilliance? Could instrumental artifacts or calibration errors mimic such extreme redshifts? Each hypothesis was tested and retested, but none explained all the observations as neatly as the dark star model. The energy ratios, the size, the lack of metallicity, all pointed to something primordial and strange. These weren't galaxies filled with countless small suns. They were singular, enormous, glowing entities unlike anything seen since. The possibility sent ripples of excitement through the scientific community. For the first time, an observation seemed to align with a theoretical prediction from the frontier of dark matter physics. If these truly were dark stars, they would represent not only a new class of celestial body, but a bridge between cosmology and particle physics, between the large-scale structure of the universe and the smallest building blocks of matter. Webb's detectors, cooled to near absolute zero, were now capturing whispers of annihilation events that took place when the cosmos was still a cosmic infant. The implications were staggering. Fries's original simulation suggested that dark stars could live for millions, even billions, of years long enough for them to grow by accreting surrounding gas, eventually becoming giants so massive that they might collapse directly into black holes without ever passing through a traditional fusion-burning phase. That process could explain the existence of supermassive black holes in the early universe, objects whose sheer scale defied all known models of stellar evolution. The idea that dark stars might serve as the ancestors of these cosmic monsters was intoxicating. The data from Webb hinted at precisely that chain of events, enormous low-temperature objects whose light would eventually fade, leaving behind invisible but gravitationally powerful remnants. Still, the story was far from over. Even with Webb's clarity, the early universe remains a murky window. Light that has travelled for 13 billion years is faint and fragile, distorted by cosmic expansion and interstellar dust. To confirm the dark star hypothesis, scientists would need not just images but spectra-detailed measurements of how these objects emit light across all wavelengths. Such data could reveal the unique energy distribution expected from dark matter annihilation, and so the search intensified. Every new observation brought the theory closer to either vindication or dismissal. But whether or not the final verdict proves these to be true dark stars, the discovery had already changed how scientists thought about the universe. It had shown that there are still phenomena waiting to be uncovered at the edge of visibility, that the cosmos may still hold forms of light born from darkness itself. In the quiet hum of Webb's instruments, in the faint red glow of the first dawn, humanity had glimpsed a truth older than stars. The possibility that even the unseen forces governing the universe have their own way of shining. To understand what makes dark stars possible, one must confront the enigma at their core: dark matter itself. It is the most abundant yet least understood form of matter in existence, a cosmic phantom that neither emits nor absorbs light but outweighs everything visible by a factor of 5. The stars, planets, and galaxies we see make up only a small fraction of the universe's mass. The rest is hidden in an invisible web that governs everything through gravity alone. Astronomers discovered its presence not by seeing it directly, but by observing its influence. Galaxies spin too fast for their visible matter to hold them together. Galaxy clusters bend light more strongly than their luminous contents can explain, and the cosmic microwave background, the faint afterglow of the Big Bang bears, the unmistakable imprint of a gravitational force that ordinary matter cannot account for. This unseen mass is dark matter, and though it has never been observed directly, its fingerprints are everywhere. It is the scaffolding of the universe, the silent architecture upon which all cosmic structure is built, yet its true nature remains an enduring mystery. Countless experiments have sought to capture it. Underground detectors buried beneath mountains, arrays of chilled crystals, particle accelerators smashing protons at near-light speeds. So far, nothing has been found. The particles refuse to reveal themselves, eluding every trap. Still, physicists persist because the evidence for their existence is overwhelming. If dark matter did not exist, galaxies would tear themselves apart, the cosmic web would unravel, and the large-scale structure of the universe would not look the way it does. Something invisible holds everything together, and that something must carry mass. Over the years, theorists have proposed many candidates. The leading one remains the WIMP, the weakly interacting massive particle. WIMPs are hypothetical particles that, as their name implies, have mass and interact through gravity and the weak nuclear force but not through electromagnetism. Because they ignore light, they're effectively invisible, drifting through ordinary matter as though it weren't there. Billions of them may be passing through your body every second without leaving a trace. Their rarity of interaction makes them extraordinarily difficult to detect, but also uniquely suited to shaping the cosmos. In the young universe, WIMPs would have been abundant, swirling within dark halos that attracted hydrogen and helium. And while their weak interactions made them elusive, those same interactions could, under the right conditions, lead to annihilation. When two WIMPs collide, they destroy each other, converting their mass entirely into energy-pure light, pure heat. This annihilation is the heartbeat of a dark star. In the earliest epochs, when densities were high, annihilations would have been frequent enough to produce steady radiation. Unlike fusion, which requires pressure and heat to ignite, annihilation simply requires proximity. If enough dark matter particles clustered in a small region, they would generate power spontaneously, even in the coldest, darkest corners of space. This property makes dark matter an almost perfect cosmic fuel source, silent, invisible, yet capable of transforming death into illumination. But it also makes it terrifyingly mysterious. No one knows what dark matter is made of, how it came to dominate the universe, or whether it might one day decay into something detectable. Its presence defines cosmic behavior, yet it lies beyond the reach of any direct experiment. Every star, every galaxy, every cluster sits within a vast cocoon of it, a gravitational fog through which the visible universe floats like dust in a beam of light. To Friis, this enigma was not just a challenge but an opportunity. If dark matter annihilation could be powerful enough to fuel a star, then the early universe might have been filled with dark light objects that glowed gently, not because of atomic reactions, but because of the invisible dance of WIMPs at their cores. This idea gave dark matter a personality, transforming it from a passive weight into an active participant in creation. For centuries, astronomers had divided the cosmos into light and darkness, the luminous and the hidden. But the notion of dark stars erased that boundary. It suggested that the dark could give birth to the light, that the universe's greatest mysteries might also be its earliest sources of brilliance. In that sense, dark matter becomes not merely a problem to solve, but a cosmic storyteller, a force that shapes both the seen and unseen, that writes its influence across billions of light years without ever showing its face. The irony of it all is profound. The thing that makes the universe visible is, in essence, invisible itself. And perhaps that is the truest reflection of reality, that the brightest lights may only exist because of the deepest shadows, and that to understand how the universe shines, we must first understand the nature of its darkness. In the ordinary universe, energy is extracted through transformation. Hydrogen becomes helium in the heart of a star, matter falls into black holes and releases radiation, and even the smallest chemical reactions rely on bonds breaking and reforming. But in the strange physics of dark matter, energy is born through destruction. When two particles of dark matter meet, they annihilate completely, erasing their mass and converting it into bursts of radiation. It is not combustion or fusion, but a total transmutation of existence into light. To imagine this process is to imagine the purest energy imaginable. No residual atoms, no ashes, no leftover fragments, just a pulse of photons where once there was mass. This annihilation is the secret engine that allows dark stars to shine. In the dense early universe, where dark matter particles were packed closely together, the probability of collision was high. Within the gravitational wells of forming halos, dark matter particles orbited and scattered until chance encounters triggered annihilation. Each collision unleashed a microcosmic explosion, releasing energy at a rate determined by the square of the particle density. The heat radiated from these events spread into the surrounding hydrogen gas, countering the force of gravity that tried to pull it inward. The result was equilibrium. Instead of collapsing violently to ignite fusion, the gas stabilized, forming a massive swollen sphere of light powered entirely by the death of invisible particles. This balance between gravitational collapse and annihilation heating defined the life of a dark star. The physics was almost poetic, a dance of forces that kept destruction and creation perfectly aligned. If the dark matter density rose, annihilation would accelerate, producing more heat and expanding the star until the density dropped again. If it fell too low, gravity would dominate, drawing more dark matter inward until the process reignited. Through this feedback, the dark star maintained a steady luminosity for millions of years. Unlike nuclear fusion, which requires precise temperatures and pressures to sustain itself, annihilation could occur in a broad range of conditions. As long as enough dark matter was present, the energy would continue to flow. The remarkable part was how little dark matter was needed. Even though WIMPs were vastly outnumbered by hydrogen atoms, their annihilations were so energetic that a tiny fraction could power an entire star. A single annihilation converted the total rest mass of two particles directly into energy, a level of efficiency that fusion could never match. In a sense, Dark stars were ultimate energy converters turning invisible matter into visible light with nearly perfect precision. This annihilation mechanism not only explained how dark stars could shine, but also provided a bridge between cosmology and particle physics. The rate at which dark matter annihilates is directly linked to its cross-section, the measure of how likely two particles are to interact. Observing dark stars and measuring their brightness could therefore yield insights into the fundamental properties of dark matter itself. Each photon emitted from a dark star could be thought of as a message from the universe's hidden sector, carrying encoded information about the physics of the unseen. This realization opened a new path for discovery. If dark stars existed, they could serve as natural laboratories for studying dark matter in conditions that can never be recreated on Earth. Yet there is a profound irony in this concept. The very process that makes dark stars luminous also seals their fate. Annihilation is finite. It consumes the fuel it depends upon. As the star radiates, it slowly depletes the reservoir of dark matter at its core. Once the annihilation rate falls below the threshold needed to balance gravity, the star begins to contract. The outer layers collapse inward, compressing the remaining gas until temperatures soar and nuclear fusion finally ignites. For a brief time, the dark star becomes an ordinary one, burning hydrogen like countless others. But by then, its mass has grown so enormous that even fusion cannot prevent its downfall. Inevitably, it collapses into a black hole, a remnant of both light and darkness. This life cycle transforms annihilation into creation on a cosmic scale. The destruction of dark matter not only produces energy, but also paves the way for the birth of the first supermassive black holes, the gravitational giants that would later anchor galaxies and shape the evolution of the cosmos. Annihilation thus plays a paradoxical role. It is both the act of erasure and the seed of permanence. Every photon that escaped from those first dark stars was a fragment of matter being unmade, a whisper of the universe's most ancient violence rendered into beauty. To think that the first light in the cosmos came not from atoms fusing, but from particles dying, is to glimpse a universe where even annihilation can be creative, where the end of one form of existence becomes the beginning of another. In this sense, dark stars embody the deepest symmetry of all, that destruction and creation are not opposites, but two expressions of the same cosmic law, the law that nothing truly vanishes, it only changes form, illuminating the darkness it leaves behind. When the first dark stars began to form, the universe was still an infant, scarcely a few 100 million years old. Space was quieter then, filled mostly with hydrogen, helium, and the elusive mist of dark matter that governed their motion. Gravity, the great sculptor of the cosmos, had only just begun to gather matter into the first halos, regions where the invisible and the visible intertwined. Within those halos, the seeds of something extraordinary began to take shape, vast glowing spheres unlike anything that would ever follow. These were the cosmic giants, the first light bringers, and they were born not from fusion but from the invisible fire of annihilation. The birth of a dark star began with the collapse of a primordial gas cloud inside a dark matter halo. As gravity pulled the hydrogen inward, dark matter particles followed, drawn toward the same dense center. The deeper they sank, the more often they collided, annihilating and releasing bursts of energy. This radiation heated the surrounding gas, halting its collapse before it could ignite fusion. Instead of forming a compact hot core, the cloud swelled into an immense cool sphere of shimmering plasma, a star that glowed softly but possessed the mass of thousands, even millions, of suns. Unlike normal stars which shine fiercely and burn out quickly, dark stars could grow without limit. As they radiated, they continued to attract more gas from their surroundings, feeding on the abundant hydrogen of the early universe. The annihilation of dark matter provided a steady source of heat that prevented the gas from collapsing into smaller fragments, allowing a single dark star to dominate its region of space. Over time, it swelled into a colossal structure, perhaps as wide as Earth's orbit around the Sun, or even larger. These giants were both delicate and monstrous fragile in their cool glow, yet immense in their scale. To an observer within one, the horizon would seem endless, a soft ocean of red light extending in every direction. Their surfaces were cool enough to touch, in theory, only a few thousand degrees, but their interiors were alive with energy. Deep inside, invisible particles met and perished, releasing light that drifted slowly outward, bathing the universe in a gentle infrared glow. For millions of years, these giants ruled the darkness. They were the first sources of sustained illumination, their light spreading across the expanding void, scattering off the newborn hydrogen and shaping the chemistry of the cosmos. The energy they emitted was weaker than the searing radiation of later stars, but because they were so vast, their total luminosity rivaled that of galaxies. In their presence, the universe's darkness thinned. The cosmic dawn had begun. As they aged, dark stars continued to grow, gathering mass from the surrounding gas clouds that still lingered in their halos. The larger they became, the more dark matter they trapped, feeding the annihilation cycle that sustained them. In this feedback loop, size begot power, and power begot further growth. Some simulations suggest that these titans could have reached masses 10 million times greater than the Sun, dwarfing any star that exists today. They were the original giants, the progenitors of everything luminous that followed. Yet their beauty was impermanent. Eventually the supply of dark matter dwindled. As the universe expanded, the density of dark matter around them thinned, and the rate of annihilation slowed. Without that internal heat, the delicate balance holding them aloft began to fail. Gravity, patient and relentless, reclaimed its dominance. The once bloated spheres started to contract, their cores growing hotter and denser until nuclear fusion finally ignited. For a brief time, the dark stars blazed with ordinary light, their soft infrared glow replaced by fierce white brilliance. But their mass was too great for stability. Fusion, instead of sustaining them, hastened their demise. The radiation pressure could not withstand the inward pull of gravity, and collapse became inevitable. In their death throes, they imploded into black holes of staggering mass, perhaps the very seeds of the supermassive black holes that now anchor galaxies across the universe. From the ashes of annihilation arose the architects of galactic structure. Each dark star that died left behind a gravitational monument capable of shaping billions of years of cosmic history. Thus, the birth of these cosmic giants was also the birth of destiny itself. The universe's first light gave rise to its first darkness, in a paradox so profound that it redefined creation. Stars born from annihilation, collapsing into voids that would one day give rise to galaxies and worlds. The echoes of their radiance still travel through space, faint but eternal, carrying the memory of a time when the cosmos was young and the boundary between light and shadow did not yet exist. To gaze upon that ancient glow through telescopes like Webb is to look back at the moment when the impossible became real, when the universe, still shrouded in darkness, found its first way to shine. In the earliest moments after the Big Bang, the universe was a sea of simplicity, an endless expanse of hydrogen, helium, and dark matter woven together by gravity's invisible hand. Over the next few 100 million years, small fluctuations in that primordial mixture began to grow, forming regions of slightly higher density that attracted more matter. These gravitational wells, composed mostly of dark matter, became the first halos, the cosmic cradles of structure. It was within these halos that the first stars, galaxies, and perhaps even the first black holes were destined to form. Yet what happened inside them defied every expectation. The halos were vast and ghostly, their dark matter invisible but dominant, accounting for about 85% of their total mass. Ordinary matter gas composed almost entirely of hydrogen and helium drifted within these halos like mist in a valley, pulled inward by the gravity of unseen particles. In most cases, that gas would cool and collapse until it ignited nuclear fusion, giving birth to the first generation of stars known as population 3 stars. But in certain halos, something different occurred. Instead of collapsing rapidly, the gas began to glow faintly, sustained by an energy source that was anything but ordinary. These were the nurseries of dark stars. Inside a forming halo, the density of dark matter was far greater than anywhere in the universe today. Billions of invisible particles moved in a gravitational dance, colliding only rarely but with immense consequence when they did. Each annihilation released a burst of energy, and though the collisions were infrequent, the sheer number of particles ensured a steady heating effect. This energy leaked into the surrounding hydrogen, counteracting the force of gravity and halting the collapse that would otherwise lead to fusion. The result was equilibrium, a cosmic truce between contraction and expansion. The gas swelled into an immense, cool, luminous body, stabilized not by thermal pressure from fusion, but by the heat of dark matter annihilation. To an outside observer, such an object would appear faint and red, its light stretched into the infrared by the vast distance of space and time. Within the halo, however, its presence transformed everything. The dark star acted as a gravitational anchor, drawing in more gas and dark matter from its surroundings, growing larger with every passing epoch. These halos, scattered like invisible seeds across the young cosmos, became the first laboratories of cosmic complexity. The process was delicate, depending on an intricate balance of conditions. If a halo was too small, it could not trap enough dark matter to sustain a dark star. If it was too large, its internal dynamics would cause the gas to fragment into smaller clumps, forming ordinary stars instead. But in just the right halos, those with masses around 1 million times that of the Sun, and with a high concentration of dark matter near the centre, the balance was perfect. Here the first dark stars bloomed, enormous and ethereal, glowing with the quiet power of annihilation. The interiors of these stars were unlike anything that exists today. In a typical star, the core is a furnace of unimaginable heat and density, where atomic nuclei collide and fuse to form heavier elements. But inside a dark star, the temperatures were lower, and the energy came not from fusion but from the slow, continuous annihilation of dark matter particles. Each event released gamma rays, electrons and positrons that scattered throughout the gas, heating it from within. Because the energy was distributed evenly, the star remained stable and diffuse rather than dense and explosive. This structure gave it a ghostly appearance, enormous but faint, radiant yet serene. These halos were the cosmic wombs of duality, places where the visible and invisible work together to forge light from darkness. Without dark matter, the gas would have collapsed too quickly. Without gas, the dark matter would have remained cold and inert. Together, they created something entirely new, an entity that could not exist without the cooperation of both realms. As time passed, these halos began to merge, forming larger and more complex systems. The dark stars within them may have drifted toward the centres, drawn by mutual gravity, eventually merging themselves to form even greater structures. Some of these mergers could have created black holes so massive that they would one day anchor entire galaxies. Thus, the first halos were not merely cradles of light, they were the blueprint of cosmic architecture. Within them, the basic pattern of the universe was set: dark matter forming the invisible skeleton, baryonic matter filling it with light, and gravity binding the two together in eternal interplay. When we look at the vast cosmic web today, with its filaments of galaxies stretching across billions of light years, we are seeing the grown-up version of those first halos. Every cluster, every star, every beam of light traces its lineage back to those ancient invisible nurseries where darkness and matter first learned to coexist. The halos of the early universe were not empty shells, they were the silent workshops where the universe learned how to build itself, turning gravity's invisible geometry into the luminous order we now call the cosmos. When the James Webb Space Telescope first opened its golden eyes to the cosmos, what it revealed stunned the world. Scattered across the deep field images were faint, glowing pinpoints, tiny crimson sparks floating at the edge of time. Astronomers called them little red dots. These weren't galaxies in the ordinary sense, nor stars as we knew them. They were too bright to be lone stars and too small to be full-fledged galaxies. Instead, they occupied a strange middle ground, as though nature herself had blurred the line between star and galaxy. The deeper scientists looked, the more baffling these red dots became. Each represented an object that existed only a few 100 million years after the Big Bang, yet they emitted as much light as an entire galaxy composed of billions of stars. Their spectra were shifted deep into the red end of the electromagnetic spectrum, a sign that they were unimaginably distant. But even after correcting for that redshift, the luminosity remained inexplicably high. They were in essence too bright for their time. These discoveries upended everything astrophysicists thought they knew about the early universe. According to standard cosmological models, it should have taken at least 1 billion years for galaxies of such brightness to form. The first stars, population 3 stars, were expected to be massive, short-lived and scattered, not concentrated into compact, intensely luminous objects. Yet here they were, shining from the cosmic dawn with a brilliance that mocked those expectations. The scientific community was divided. Some argued that the red dots must be small, early galaxies undergoing extreme bursts of star formation. Others suspected gravitational lensing massive objects between us and the red dots, magnifying their light, making them appear brighter than they really were. But neither explanation fit perfectly. The spectral profiles of these dots lacked the strong ultraviolet signatures typical of starburst galaxies, and their shapes were too symmetric, their energy distribution too smooth. Something about them felt fundamentally different. When Catherine Fries and her team examined the data, a thrilling thought emerged. These could be the long-predicted dark stars. The infrared signatures matched what her models had forecast years before: large, cool, red, and radiating softly across wavelengths invisible to the human eye. Their light wasn't the harsh white glare of fusion, but a more muted, diffuse glow consistent with the thermal emission of dark matter-powered objects. Webb's high-resolution instruments made it possible to measure the energy spread of these red dots in unprecedented detail. Their temperatures appeared to hover around several thousand Kelvin too cool for typical young stars, but perfect for dark stars. The sheer size required to produce such luminosity at those temperatures implied radii tens of thousands of times larger than the Sun's. No ordinary stellar cluster could mimic that effect. If these were indeed single objects, they were the largest stars the universe had ever known. The little red dots, then, might not be galaxies at all, but solitary, swollen giants' cosmic beacons powered by the annihilation of dark matter deep within. The implications were staggering. If even a handful of these red dots turned out to be dark stars, it would mean that the early universe was far more exotic than anyone had imagined. Instead of being filled solely with collapsing hydrogen clouds and primitive galaxies, it may have been dotted with these enormous, softly glowing orbs light born from invisible violence. Some astronomers resisted the idea, insisting that the notion was too speculative, but others pointed out that every alternative explanation seemed even more implausible. The simplest solution, according to Occam's razor, might be the radical one, that the dark stars Fries had envisioned actually existed, and that Webb had finally glimpsed them across the abyss of cosmic time. In this new light, the red dots became more than curiosities. They became cosmic fossils, remnants of the first chapter of creation. Their discovery also offered potential answers to other long-standing mysteries. For instance, the existence of supermassive black holes so soon after the Big Bang has always puzzled scientists. How could black holes billions of times the mass of the Sun form so quickly? If dark stars grew enormous before collapsing, they could have seeded these early behemoths, solving one of cosmology's greatest riddles. The little red dots might thus represent both the beginning and the end of the first stellar era. Stars that lived not through fusion, but through annihilation, and that died not as remnants but as gravitational kings. Observing them today is like peering into a dream preserved in light, a vision of the universe when it was still learning how to shine. In those tiny crimson points, suspended across the blackness of space, lies the memory of a time when creation and destruction were indistinguishable, when darkness itself learned to glow, and when the first true lights of existence flickered into being not from atoms colliding, but from the invisible fabric of the cosmos tearing itself apart. Every light in the universe eventually dims, and even the greatest giants must one day fall. The dark stars, for all their ethereal beauty and impossible power, were no exception. Their brilliance came not from the endless fire of fusion, but from a rarer, finite source dark matter, annihilation. For millions of years this process sustained them, holding gravity at bay and keeping their enormous forms inflated like cosmic balloons. But as the dark matter supply dwindled, the balance that had defined their lives began to unravel. Gravity, patient and relentless, reclaimed its dominance. Slowly, imperceptibly at first, the vast hydrogen envelopes that had been puffed up by annihilation began to contract. As the gas compressed, temperatures at the core rose, and for the first time in their long existence, these stars approached the threshold of nuclear ignition. What happened next was a transformation both magnificent and fatal. When the core temperature reached millions of degrees, hydrogen fusion began, and the dark star was reborn as a conventional one. Yet this new phase was short-lived, a final burst of brilliance before the end. These stars were simply too massive to survive the violence of their own energy. Fusion, instead of stabilizing them, acted as a trigger for collapse. Their enormous gravitational pull overwhelmed the outward pressure from nuclear reactions, and the equilibrium shattered. The Titan began to implode. As the outer layers fell inward, the density and temperature at the core skyrocketed until even light could no longer escape. The result was catastrophic and absolute: the birth of a black hole. Thus ended the era of the dark stars, and thus began a new one defined by darkness of another kind. The black holes that emerged from these collapses were not ordinary by any measure. They were colossal, perhaps hundreds of thousands or even millions of times the mass of the Sun. In an instant they became the gravitational anchors of the young universe, shaping the formation of galaxies and regulating the growth of cosmic structure. It is these remnants that many scientists now suspect became the seeds of the supermassive black holes we observe at the centers of galaxies today, objects so vast that nothing, not even light, can escape their pull. The transformation from dark star to black hole was a perfect cosmic irony. What had once been powered by the annihilation of invisible matter now became a monument to its absence, a well of infinite darkness carved from light itself. Yet even in death the dark stars were not silent. Their collapse sent ripples through space-time gravitational waves that echoed across the cosmos, carrying with them the memory of their violent end. These signals may still be detectable today, faint tremors in the fabric of reality left behind by the fall of the universe's first giants. If observed, they would serve as direct evidence of their existence, the final whisper of a vanished age. But the legacy of the dark stars extended far beyond their immediate collapse. The black holes they left behind became engines of cosmic transformation. As matter spiraled into them, it heated and radiated, releasing energy that influenced the evolution of the galaxies forming around them. Some of these black holes likely merged with others, creating even larger gravitational monsters. Over billions of years they would come to dominate the hearts of galaxies, including our own Milky Way. In this way, the death of the dark stars gave birth to the large-scale structure of the modern universe. Their annihilation-powered lives had illuminated the cosmic dawn. Their gravitational deaths would sculpt the cosmic day. The collapse of the Titans marked the transition from the universe's infancy to its adolescence, from the first light to the first structures capable of shaping their surroundings. Each death was both an ending and a beginning, a bridge between two eras of cosmic evolution. The story of these stars is one of paradox and symmetry. They began as entities sustained by destruction, dark matter annihilating itself, and ended by becoming the most perfect expression of destruction known: black holes, where space and time themselves collapse. In both forms they embodied the same principle, that creation and ruin are inseparable, that every source of light is bound to become its own shadow. The physics of their downfall also carries a haunting elegance. As their outer layers cascaded inward, the density became so extreme that quantum effects and relativity danced together, shaping a singularity, a point where all equations break down. No human mind can truly comprehend what happens there, where mass becomes pure curvature of space-time. Yet from that incomprehensible void, order would eventually emerge. Galaxies would gather around these dark hearts, stars would form in their wake, and the universe would continue to evolve in complexity and beauty. The collapse of the Titans was not the end of the cosmic story, but the end of its prologue. Through their deaths, the universe gained the engines that would one day give rise to everything we know. Even now, billions of years later, every galaxy we see, every star we study, owes its existence to those first colossal deaths. The universe, it seems, learned early that from the fall of giants comes the birth of worlds. As astronomers pushed their instruments further into the past, they began to uncover a cosmic paradox that defied all logic. Scattered across the young universe, less than 1 billion years after the Big Bang, were monstrous black holes, some containing billions of solar masses. These behemoths, known as quasars, blazed with the light of entire galaxies as they devoured surrounding gas and dust, yet their very existence should have been impossible. According to every conventional model of astrophysics, there simply had not been enough time for such giants to form. The birth of a black hole requires the death of a massive star, and the growth of that black hole depends on the slow process of accretion, the gradual feeding on matter drawn by gravity. Even under the most optimistic conditions, the math didn't work. The universe was too young, too empty, too chaotic. And yet the observations were irrefutable. Quasars shining from just a few 100 million years after the Big Bang were real, their spectra recorded, their light unambiguous. These early monsters demanded explanation. Where had they come from? How could something so massive appear so soon? It was as if the universe had skipped a chapter in its own story. This mystery became one of the great puzzles of modern cosmology. Scientists proposed every possible mechanism to account for the early appearance of supermassive black holes. Perhaps they had formed from the direct collapse of enormous gas clouds, bypassing the usual stellar phase. Perhaps they had grown through runaway mergers of smaller black holes within dense star clusters. Or perhaps the physics governing accretion was more efficient in the early universe, allowing black holes to consume matter faster than we had ever imagined. Yet none of these explanations felt entirely satisfactory. Each required conditions so specific and improbable that they bordered on coincidence. Then, from the theoretical shadows came an idea that seemed almost poetic in its simplicity. What if these early monsters were the descendants of dark stars? The theory fit beautifully. If dark stars could grow to millions of solar masses before collapsing, they would provide the perfect seeds for the supermassive black holes observed by Webb and other telescopes. Their immense initial size would eliminate the need for rapid, implausible growth. Their formation in the earliest halos would naturally place them in the right locations and epochs. The paradox of early black holes, long unsolved, began to make sense. The numbers aligned with uncanny precision. A dark star powered by dark matter annihilation could live for millions of years while continuously accreting gas. When its dark matter fuel finally depleted, it would collapse almost instantly into a massive black hole. Unlike the small remnants left behind by ordinary stars, these would begin their existence already enormous, 10,000, 100,000, or even 1,000,000 times the mass of the Sun. From there, natural accretion could easily push them into the supermassive range by the time the universe was less than 1 billion years old. The hypothesis also explained why quasars in the early universe appeared to cluster around regions rich in dark matter. These were precisely the halos where dark stars were most likely to have formed. In this framework, the universe's first light and its first darkness were intimately linked, the luminous phase of the dark star leading seamlessly into the abyss of the black hole. Still, skepticism lingered. Many astronomers found the idea alluring but difficult to verify. After all, dark stars were still hypothetical. Their signatures in Webb's data were tantalizing but not yet conclusive. To accept them as the origin of supermassive black holes required a leap of faith, albeit one grounded in increasingly persuasive evidence. Yet the elegance of the idea could not be ignored. It unified disparate mysteries under a single explanation, connecting dark matter physics with galactic evolution in a way no other model had achieved. The paradox of early monsters, once a source of frustration, now looked like a natural outcome of the universe's hidden architecture. If this interpretation proves correct, it would mean that the universe's greatest destroyers were born from its most mysterious substance. Dark matter, long thought to be passive and inert, would emerge as the architect of both creation and annihilation. It would mean that the very force responsible for holding galaxies together also gave birth to the entities that now sit at their hearts. The irony is profound. The darkness that permeates the cosmos may have been the midwife of its brightest fires and deepest voids alike. The early monsters, those quasars blazing from the edge of time, are not violations of physics but confirmations of a deeper one, a testament that the cosmos began not in simplicity but in paradox. As telescopes continue to peer further back, each new discovery seems to reinforce this vision. The young universe was not a quiet nursery of small stars but a tempestuous crucible of giants, collapsing and consuming, shaping the future with every flash of annihilation. The paradox is no longer one of existence, but of understanding. The universe is not just older than we imagine, it is stranger than we ever dared to believe. In the traditional understanding of astrophysics, there is a limit to how fast a black hole can grow, a boundary known as the Eddington limit. This theoretical ceiling describes the point at which the outward pressure of radiation from infalling matter balances the inward pull of gravity. If a black hole accretes material faster than this limit allows, the resulting radiation would blow away the remaining gas, halting further growth. This principle, elegant in its simplicity, governs the evolution of stars and black holes alike. Yet the early universe appears to have defied it. Observations of supermassive black holes less than 1 billion years after the Big Bang suggest that somehow nature broke the rules. For these cosmic titans to have reached billions of solar masses so quickly, they would have had to consume matter at rates many times higher than the Eddington limit permits. Such rapid feeding should have been impossible, and yet the quasars Webb and other telescopes have revealed prove otherwise. Something allowed those black holes to grow unchecked. Perhaps, scientists theorized, the Eddington limit was never a true barrier, only a guideline that could be bypassed under extreme conditions. The question was, what conditions could those have been? For ordinary black holes, the only path to super-Eddington growth involves the formation of dense accretion disks where matter funnels inward faster than radiation can escape. The intense gravity near the event horizon bends light, trapping it long enough for additional matter to fall in. This process, known as photon trapping, allows the black hole to gorge itself faster than it should be able to. But even with such mechanisms, the rate of growth in the early universe remains baffling. The numbers still don't add up, unless the initial black holes were already enormous when they formed. Here, the dark star hypothesis provides a natural solution. If the first black holes were born from the collapse of dark stars millions of solar masses in size, then they would begin their lives already far above the threshold needed to become supermassive within a cosmic blink. They would not need to break the Eddington limit. They would begin closer to the finish line. Their early growth could then proceed more modestly, in accordance with known physics, producing the quasars observed at redshifts of 7 and beyond. In other words, what appeared to be a violation of cosmic law may simply be a misunderstanding of initial conditions. The dark stars in dying had done the heavy lifting. But there is another possibility, more provocative still. The physics of dark matter annihilation itself may have altered the rules of radiation pressure. In the final stages of collapse, as a dark star exhausted its supply of annihilating particles, the balance between heating and cooling would have shifted dramatically. Instead of a sudden implosion, there might have been a chaotic interplay of forces that allowed some of the collapsing mass to continue feeding energy into the system even as the black hole formed. This residual annihilation could have created a temporary phase of hyperaccretion, a moment when matter and radiation coexisted in a state far beyond the classical Eddington limit. If this occurred, the newborn black holes would have emerged already surrounded by dense disks of gas superheated by annihilation energy, providing the perfect conditions for runaway growth. To the universe, it would have looked like a storm of creation, invisible to all but the faint whispers of gravity and light. Such a mechanism would mean that the Eddington barrier was never truly broken but redefined. In the environment of the early cosmos, where densities were higher and dark matter more abundant, the interplay of forces may have allowed for modes of accretion that no longer exist today. What we now interpret as impossible might simply have been natural in those primordial times. The universe, after all, plays by different rules when it is young and hot. These considerations have profound implications. They suggest that the earliest epochs of cosmic evolution cannot be understood by applying modern conditions retroactively. The same physical constants remain, but their interactions unfold in different contexts, densities, temperatures, and particle populations that no longer exist. The Eddington limit, in that sense, is a rule written for a later, cooler universe. In the blazing youth of creation, the cosmos may have been wild and permissive, allowing growth and transformation on scales unimaginable today. What we call paradox may simply be memory. The early monsters, the quasars that challenge our equations, may therefore be less an anomaly than an echo, a sign that the universe's first generation of light and darkness operated under a physics we're only beginning to rediscover. The collapse of dark stars, the birth of their black hole heirs, and the violent hunger that followed were all part of a seamless process. The cosmos creating the conditions for its own illumination. To break the Eddington barrier, then, is not to defy nature but to reveal her deeper logic, that under certain primordial circumstances, creation has no limits, and the laws that later constrain the universe once allowed it to grow with boundless incandescent freedom. In the search to explain the sudden appearance of immense black holes at the dawn of time, one theory emerged as both daring and elegant: the concept of direct collapse. Instead of beginning as small remnants of ordinary stars that slowly fatten through accretion, these early titans might have skipped every intermediate step, forming directly from massive clouds of primordial gas collapsing under their own gravity. The idea of direct collapse offers a shortcut in cosmic evolution, a mechanism that bypasses the long, inefficient process of star formation and stellar death entirely. Rather than being born from a star's ashes, a black hole could emerge whole, forged directly from the raw materials of the early universe. But the question has always been, how could a gas cloud collapse into a black hole without fragmenting into smaller stars first? Normally, as hydrogen cools, it breaks apart into dense knots that ignite fusion and create conventional stars. To form a single massive black hole, that fragmentation must somehow be suppressed. For decades, this problem remained unresolved. It seemed that the physics of cooling inevitably led to many small stars, not one enormous one. Then the dark star hypothesis appeared to offer an unexpected bridge. If dark matter annihilation could prevent cooling by heating the gas cloud from within, it could delay or entirely prevent fragmentation. Instead of forming hundreds of small stars, a single, vast body would emerge. A dark star so massive and diffuse that, when its dark matter supply was exhausted, it would collapse directly into a black hole. In this way, dark stars provided a natural realization of the direct collapse scenario. Their internal physics sustained by annihilation, heating created the perfect conditions for a smooth, monolithic collapse once equilibrium failed. The transition from light to darkness would be instantaneous. No supernova, no dispersal of elements, no violent explosion, just implosion, gravity reclaiming everything it had momentarily lent to illumination. The result would be a black hole already millions of solar masses in size, born full-grown into a young and hungry universe. Such an event would not only explain the presence of quasars at extreme redshifts, but also illuminate the origins of galactic structure. These early, massive black holes would have acted as gravitational centers around which gas and dust could coalesce, forming the first proto-galaxies. The direct collapse model, when powered by dark matter physics, thus merges two of cosmology's deepest mysteries, the nature of dark matter and the origin of structure, into a single self-consistent story. What makes this theory so compelling is its simplicity. The same forces that shape the large-scale universe gravity and annihilation work together in miniature to birth its most enigmatic objects. The dark matter halo provides the gravitational scaffold, the annihilation provides the heat to resist fragmentation, and when that energy source finally runs out, the inevitable collapse produces the seeds of cosmic architecture. This elegant interplay removes the need for improbable rates of accretion or exotic new physics. It requires only that dark matter behave as it already seems to in every other context. Observations by the James Webb Space Telescope have lent further weight to this narrative. The discovery of luminous objects that are both too massive and too early to be conventional galaxies hints strongly at direct collapse events. Their red, diffuse light profiles and enormous inferred masses are precisely what one would expect from dark stars on the verge of implosion. In a sense, Webb may have caught the universe in the act of performing this primordial transformation, the quiet moment before the collapse, when annihilation still holds gravity in check and the cosmos itself stands poised between illumination and shadow. The implications of this are profound. If dark stars truly mark the beginning of direct collapse black holes, then our entire cosmic history must be rewritten. The first galaxies would not have emerged from clusters of small stars merging together, but from the gravitational wells of collapsed giants. The elements that later formed planets and life would have been forged not in supernova explosions, but in the slow accretion disks around these newly born black holes, where matter heated and radiated as it spiraled inward. Even the very notion of what it means for the universe to begin to shine changes under this view. Light and darkness become partners in creation, each stage of collapse and annihilation, giving rise to new structures, new possibilities. The direct collapse solution, therefore, is not just a technical model, it is a philosophical revelation. It suggests that complexity can arise not through gradual accumulation, but through decisive transformation. That sometimes the universe does not build step by step, but leaps into existence whole. A dark star collapsing into a black hole is one such leap, a cosmic heartbeat where all the potential energy of creation is released in a single silent fall. In that fall, the universe learns how to build itself anew, turning invisible matter into the foundations of galaxies, into the engines of light that will one day illuminate the sky. As the early universe matured, the black holes born from collapsing dark stars did not remain isolated. Gravity, the great gatherer, drew them together just as it had once assembled the first clouds of hydrogen and helium. The cosmos, still dense and turbulent, became a vast stage for their convergence. These young black holes drifted through merging halos of dark matter, embedded within streams of gas that flowed along the cosmic web. When two such halos collided, their central black holes were brought into proximity, and a new kind of cosmic dance began, a dance of merging shadows. Unlike the quiet deaths of their dark star ancestors, these encounters were violent symphonies of gravity and energy. As the black holes spiraled toward each other, they twisted the very fabric of space-time, generating waves that rippled outward at the speed of light. These gravitational waves carried away angular momentum, allowing the black holes to draw ever closer until, in a final moment of unimaginable force, they collided and merged into a single, even more massive entity. The event would have been invisible to any observer, yet its effects would reverberate across the universe. The merged black hole, now larger and hungrier than before, became a gravitational anchor for the young galaxies forming around it. Streams of matter swirled toward its event horizon, heating as they fell and producing torrents of radiation. The surrounding regions glowed with energy, and outflows of charged particles carved jets across thousands of light years. What had once been the dark heart of a single dying star was now the blazing core of a proto-galaxy. Through these mergers, the architecture of the universe began to take shape. Each collision released a storm of gravitational waves, subtle yet persistent, a cosmic heartbeat that still echoes faintly today. Instruments like LIGO and the upcoming LISA Observatory are designed to listen for these whispers-relic signals from the universe's earliest epoch, faint traces of the time when the first black holes were finding each other in the darkness. Detecting such waves would not only confirm the existence of dark star remnants, but also provide a direct glimpse into the processes that built the first galaxies. The merging of black holes is not merely a byproduct of cosmic evolution, it is one of its engines. Each union transforms chaos into structure, converting the potential energy of separation into the kinetic energy of creation. The new black hole that emerges from a merger is not simply a sum of its parts. It carries a new spin, a new orientation, a new gravitational field that influences everything around it. Over time, as more halos and black holes merged, the cosmic web grew richer and more intricate. The early universe transitioned from a scattered collection of glowing spheres into a connected network of galaxies, each with its own dark nucleus. The dark matter that once powered the first light now served as scaffolding for this grand structure, guiding the motions of gas and stars like invisible threads pulling the cosmos into order. But within that order, chaos still ruled. Mergers were messy, asymmetric, and often cataclysmic. Some collisions sent black holes recoiling through their host galaxies at incredible speeds, ejected by the recoil of gravitational wave emission. Others triggered bursts of star formation, as tidal forces compressed nearby gas clouds. The interplay between destruction and creation repeated itself at every scale. Dark stars became black holes collided and birthed galaxies, and galaxies merged to form clusters. The entire universe was a symphony of merging shadows, each note struck by gravity's hand. This process also laid the groundwork for the universe we see today. The supermassive black holes that now sit at the centers of galaxies like the Milky Way are the end result of countless mergers stretching back billions of years. Their origins lie in the dark star epoch, but their evolution is written in waves that ripple through space-time even now. Every gravitational wave detected today is, in a sense, a message from that ancient era, a remnant vibration of the universe learning how to organize itself through collapse and collision. The beauty of this cosmic cycle lies in its inevitability. Once the first black holes existed, their mergers were destined. Gravity never forgets, never relents. Over aeons, it brings all things together, erasing separation and weaving matter into ever larger, more complex forms. The merging shadows of the early cosmos were not acts of destruction, but of synthesis. They were the universe's way of sculpting permanence out of impermanence, order out of the entropy of expansion. In their silent union, they created the scaffolding of the galaxies we now inhabit, and seeded the universe with the patterns that would echo through time. Every atom, every photon, every breath we take ultimately traces its lineage to that era of cosmic merging. From the fall of the first dark stars to the union of their remnants, the universe's story is not one of isolation, but of gathering of shadows, finding each other in the dark and becoming light once more. The phrase "a cosmic dawn" once evoked a simple picture, the moment when the first ordinary stars ignited, ending the primordial darkness and filling the universe with light. For decades, astronomers imagined that after the Big Bang, the cosmos drifted through a long silent age before the familiar processes of stellar formation began. Hydrogen cooled, gravity pulled it together, and the first generation of stars population 3 flared to life, their ultraviolet light reionizing the universe and making it transparent. It was a beautiful story, elegant and complete, but perhaps not entirely true. The discoveries made by the James Webb Space Telescope and the revival of Catherine Freese's dark star theory have forced a profound reconsideration of this narrative. The cosmic dawn, it seems, may not have begun with fusion, but with annihilation. The first sources of light may have been not stars as we know them, but enormous cool giants powered by the invisible energy of dark matter. This idea rewrites not only the timeline of the early universe, but the very nature of how light first emerged from darkness. For if dark stars truly existed, then illumination began earlier than anyone thought, perhaps within just a few 100 million years after the Big Bang. Their soft infrared glow would have filled the young cosmos, a gentle radiance rather than the harsh glare of later, fusion-driven stars. The night sky of that ancient era would have been tinted in deep crimson, dotted with vast, dim spheres that shimmered like embers scattered across infinity. These early lights, though cooler and subtler than their successors, would have changed everything. Their radiation would have slowly warmed and ionized the surrounding hydrogen, subtly altering the chemistry of the universe. They would have sown the first hints of structure, guiding the flow of gas and dark matter that would later form galaxies. The cosmic dawn, then, was not a sudden sunrise but a gradual awakening, one that began with the slow-burning fires of annihilation rather than the explosive ignition of fusion. This reframing carries enormous implications for cosmology. If dark stars predated normal stars, then the epoch of reionization, the period when the universe transitioned from opaque to transparent, may have been driven, at least in part, by their light. The timelines astronomers have constructed from cosmic background radiation and early galaxy surveys might need to be shifted. Moreover, if dark stars were common, they could explain some of the anomalies in the cosmic infrared background. The faint, diffuse glow observed even in regions devoid of galaxies. That lingering light could be the fossil illumination of dark stars, still echoing across billions of years. In this new vision, the cosmic dawn becomes a layered process. First came the dark stars, vast and cool, powered by the death of invisible particles. Then, as they collapsed into black holes, their gravitational influence sculpted the formation of galaxies and clusters. Only later did conventional stars take over, their fierce ultraviolet radiation reionizing the universe and setting the stage for the cosmic noon, the era of peak star formation that followed. The dark stars thus become the missing link between the simplicity of the Big Bang and the complexity of the modern cosmos, the transitional phase that made all subsequent evolution possible. Rethinking cosmic dawn in this way also changes our philosophical perspective. It suggests that the universe's first light was not an act of spontaneous creation, but of transformation, that darkness itself gave birth to brightness, that annihilation became the instrument of illumination. This notion resonates far beyond physics. It implies that the boundary between destruction and creation, between death and birth, is not as rigid as it seems. On a cosmic scale, the same processes that erase matter can also generate beauty. In a very literal sense, the universe learned to shine by consuming its own shadow. The observational implications of this are just beginning to unfold. Astronomers are now re-examining Webb's earliest data, searching for more of the red dot objects whose properties align with dark star predictions. The patterns of their spectra, the shapes of their halos, the distribution of their brightness all may help distinguish them from early galaxies. If enough examples are found, the case for a redefined cosmic dawn will grow unassailable. Already new simulations are being developed to model how dark stars might have influenced the formation of subsequent generations of stars. Preliminary results suggest that their presence could explain the surprising abundance of massive galaxies at early times, a discovery that initially seemed to contradict the standard cosmological model. What once appeared as a challenge to theory may in fact be its missing piece. The more we look back, the more the universe insists that its beginnings were stranger, gentler, and more complex than we imagined. Rethinking the cosmic dawn means embracing that strangeness, acknowledging that the first light was not a single moment, but a continuum, a long and luminous unfolding, written in both visible and invisible ink. In that realization lies a kind of poetic symmetry, that even before the first true stars ignited, the universe already knew how to glow, not from the fire of atoms, but from the quiet radiance of the unseen. Long before the galaxies we now see had formed, before the universe was rich with metals, planets, and familiar chemistry, light itself was a rare and precious thing. The early cosmos, though vast, was almost entirely dark, a sea of hydrogen and helium adrift in a fog of cold radiation. For hundreds of millions of years after the Big Bang, this darkness was nearly absolute. Photons from the cosmic microwave background had long since stretched into the far infrared, too faint to illuminate anything. The first sources of new light would have to be born from matter itself, emerging from the slow choreography of gravity and energy. Yet when the first illumination finally came, it may not have been from the fusion of atoms, but from something deeper and stranger, the invisible dance of dark matter annihilation. This was the true birth of light, not the brilliance of familiar stars, but the awakening of luminosity from the unseen. In the silence of the primordial night, halos of dark matter gathered like invisible seeds, their gravitational pull drawing in clouds of hydrogen gas. As the gas sank into these wells, its density rose, and dark matter particles within the halo began to collide. Each collision released a burst of energy that heated the surrounding gas, halting its collapse. The balance between gravity pulling inward and dark matter heating outward gave rise to a new kind of equilibrium, a living equilibrium, sustained not by fusion, but by the annihilation of the invisible. Within these halos the first luminous bodies appeared, the dark stars. Their light was faint, cool, and red-shifted, but it was light nonetheless. The universe, once black and silent, began to glow. These early beacons were unlike any stars that followed. They were vast millions of times the size of our Sun, and so diffuse that their outer layers could have stretched far beyond the orbit of modern planets. Their temperatures were gentle compared to the blistering heat of later stars, but their surface area was so immense that they shone brightly across the cosmos. In their presence, darkness itself seemed to thin. The photons they emitted scattered through the surrounding hydrogen, creating the first bubbles of faint ionization. Though small at first, these bubbles grew, overlapping and merging, subtly transforming the cosmic environment. The birth of light was not a sudden explosion, but a gradual unveiling, a slow burn that spread outward from countless points across the universe. Each dark star was a lantern in the fog, its glow reaching across hundreds of light years, its influence reshaping the chemistry of space. The energy from their annihilation-driven cores did more than illuminate. It began the slow alchemy that would make all later structure possible. The heat from dark stars prevented the gas in their surroundings from collapsing too quickly, delaying the onset of normal star formation. This delay gave time for the first massive halos to grow large enough to support the birth of galaxies. In that sense, the light from dark stars was both creative and restraining, both midwife and guardian. The irony is profound. By shining softly, they made it possible for the universe to one day blaze with intensity. When their dark matter fuel finally ran out, they collapsed into black holes, and in doing so they gave birth to another kind of light, the radiance of accretion. Gas falling into these newborn black holes heated to millions of degrees, emitting torrents of high-energy radiation. Thus, the end of the first light became the beginning of the second. The cosmos transitioned from the warm glow of annihilation to the fierce glare of infall. From this cycle, the first quasars would eventually arise, blazing so brightly that they could outshine their host galaxies. The universe, having learned how to produce light once, now repeated the lesson in more dramatic form. The birth of light, then, was not a single event but an ongoing transformation, a relay race between different forms of energy and matter. First dark matter, then baryons, first annihilation, then fusion, first the quiet red glow, then the roaring blue-white blaze. Each stage depended on the one before, building complexity through repetition and refinement. The light we see from the earliest epochs of time is the fossil record of this process, a message from a universe discovering its own brilliance. To modern observers, that light carries meaning far beyond its photons. It encodes the laws of physics, the fingerprints of matter and energy as they learn to coexist. Every wavelength, every redshift tells a story of balance and change. The photons that now strike our telescopes have travelled for over 13 billion years, crossing the expanding void to whisper of that first dawn. They are survivors of annihilation, messengers from an age when light itself was an act of defiance against nothingness. In understanding them, we glimpse the universe not just as it was, but as it became aware of its own luminosity. The birth of light was the first moment of self-recognition in the cosmos, a realization, written in energy, that even in darkness there lies the power to shine. Once the first light broke through the cosmic darkness, the universe entered a brief but magnificent era, the Age of Giants. It was a time when stars dwarfed anything that exists today, when the laws of scale seemed to bend under the raw abundance of matter and gravity. These were the primordial titans, vast ethereal spheres powered either by nuclear fusion or by the mysterious energy of dark matter annihilation. They lived short, furious lives, and their deaths would define the future of everything that followed. In the early epochs, conditions favoured enormity. The universe was denser, and the gas clouds from which stars formed were almost entirely composed of hydrogen and helium. With no heavy elements to aid cooling, the collapsing gas could not fragment easily. Instead of forming many small stars as in later epochs, the gas gathered into single massive clumps, sometimes hundreds or even thousands of solar masses in size. Gravity worked unopposed, driving the creation of these cosmic behemoths. They burned hot and fast, their fusion reactions consuming fuel at incredible rates. Their ultraviolet light ionized the surrounding medium, clearing bubbles in the intergalactic fog and contributing to the great reionization that eventually made the universe transparent. Yet among these fiery giants, another kind of star shone more quietly, with an entirely different power source. These were the dark stars, the slow giants, vast and cold compared to their nuclear cousins, but no less awe-inspiring. Instead of burning hydrogen, they were sustained by the annihilation of dark matter particles trapped within their cores. The balance of this annihilation heating against gravity's inward pull gave them lifetimes far longer than those of normal massive stars. For millions of years they glowed softly in the infrared, their surfaces cooler, but their bodies immense, so large that one could have swallowed our entire solar system. This coexistence of two kinds of giants, the fusion-born and the annihilation-fed, marks the most mysterious chapter in cosmic history. It was a competition of light and longevity, of brightness and endurance. The ordinary population 3 stars blazed with fierce energy, but lived only a few million years before collapsing or exploding as supernovae. The dark stars, by contrast, endured in relative calm, drifting through the expanding cosmos like red ghosts. Their light was gentle but persistent, their presence subtle yet transformative. In those early millennia, the universe was a canvas of contrasts. Brilliant bursts of blue-white radiation from fusion stars interspersed with the deep, ruddy glow of annihilation giants. Together they began to shape the cosmic environment, enriching it both with energy and, later, with elements. When the massive fusion stars died, they exploded violently, scattering the first heavy atoms into space carbon, oxygen, iron. The dark stars, when they finally exhausted their dark matter supply, skipped the explosive phase altogether, collapsing directly into black holes. The interplay between these two deaths, one dispersing matter, the other condensing it, would establish the dual pathways of cosmic evolution, the chemical and the gravitational. The heavy elements from the fusion giants seeded the birth of later generations of stars and planets, while the black holes born from dark stars became the anchors of galaxies. This dynamic balance, the spreading and the gathering, set the rhythm for all that followed. During the Age of Giants, the universe grew from a simple, homogeneous expanse into a landscape of complexity. Halos merged, gas cooled, and filaments of the cosmic web began to glow faintly under the influence of radiation. The first galaxies were forming, though they were primitive and clumpy. In their centres, the black holes left by dark stars began to feed, drawing in matter and growing into the first quasars. Each of these titanic events, each star's birth and death, added a new layer to the unfolding story of creation. To an observer within that epoch, if one could have existed, the night sky would have been both alien and breathtaking. Massive stars clustered like pearls in chains along filaments of gas. Supernovae erupted with blinding intensity, briefly outshining entire galaxies. Between them floated the red, swollen dark stars, their glow steady and haunting. It was a sky of constant transformation, where every light heralded both an end and a beginning. This was the age when the universe discovered abundance, when scale ceased to be modest, when creation operated at its most extravagant, and yet it was fleeting. As heavy elements accumulated and cooling became more efficient, the formation of such colossal stars dwindled. The cosmic environment evolved, favouring smaller, more stable stars like those that populate galaxies today. The giants vanished, their time complete, leaving behind the structures that would persist for billions of years. But though they are gone, their legacy endures in every corner of the cosmos. The iron in our blood, the calcium in our bones, the black hole at the heart of the Milky Way all trace their origins to that brief era of cosmic excess. The Age of Giants was both the universe's first experiment in creation and its first lesson in impermanence. Through their birth and their fall, the universe learned how to recycle itself, how to turn death into new possibility. The giants may be gone, but their echoes are everywhere, written in light, matter, and the silent pull of gravity that still binds the stars. Billions of years after the Age of Giants faded into history, their light still travels through space stretched, cooled, and dimmed by the relentless expansion of the universe. What began as the soft crimson glow of dark stars and the fierce blue blaze of their fusion-born cousins has now been redshifted far into the infrared, forming a ghostly background that pervades the cosmos. This faint radiation, the cosmic infrared background, is the lingering memory of the first lights ever to shine. Every photon within it carries a story older than galaxies, older even than time as we experience it, a whisper from the universe when it was only beginning to learn the art of illumination. To modern astronomers, these echoes are priceless clues. Unlike visible light, which is easily scattered or absorbed by dust, infrared radiation slips through the cosmos almost unhindered. It becomes a time capsule, preserving traces of ancient structures and processes otherwise long lost. The James Webb Space Telescope was built precisely to listen to this ancient song, to detect the faint echoes of the first stars and galaxies, and to distinguish between the light of ordinary matter and that of more exotic origins. And in doing so, it has revealed a cosmos far richer and stranger than expected. The deep-field images captured by Webb show not only galaxies beyond imagination, but also a diffuse haze of unresolved light, too bright, too structured, too ancient to be explained by known populations of stars. This glow, faint yet pervasive, might well be the collective afterglow of dark stars. Their long, cool lifetimes and immense sizes would have generated exactly this kind of infrared signature, a smooth background with subtle variations corresponding to the clustering of early dark matter halos. In essence, the universe itself may still be softly lit by the remnants of their annihilation-powered radiance. For decades, astronomers puzzled over this excess infrared light. Conventional models of early star formation could not account for its brightness or its uniformity. Some speculated it came from faint, undetected galaxies. Others blamed interstellar dust scattering distant starlight. But the spectral fingerprints didn't fit. The distribution of the glow followed the large-scale pattern of dark matter, more closely than that of baryonic structures. It was as though the universe's invisible skeleton had once shimmered faintly, and that shimmer still lingered. If dark stars truly existed, Their light would now fill the cosmos as a subtle background hum, a relic of the time when annihilation first gave birth to luminosity. Detecting that hum is one of modern cosmology's great challenges. The signals are faint, buried beneath the foreground emissions of nearer galaxies and the noise of interplanetary dust. Yet by carefully subtracting known sources, astronomers can tease out the residual patterns. What remains is a diffuse glow with precisely the spectral shape expected from dark star populations. This has led some to propose that we are already seeing their afterimage, that the echoes of the first annihilation-driven lights are woven into the very fabric of the infrared sky. To study these echoes is to peer into the threshold between darkness and light. Each photon that arrives in Webb's detectors has travelled across 13 billion years, carrying with it not just energy but information about temperature, density, and even the nature of dark matter itself. The colour and intensity of the infrared background encode how efficiently dark matter annihilated, how long dark stars lived, and how they distributed themselves across the early cosmic web. By unravelling this data, scientists hope to turn the universe's oldest light into a map of its invisible foundations. There is something profoundly moving about this pursuit. The photons striking our instruments today began their journey when the universe was less than 0.1% of its current age. They passed through epochs of rionization, through the formation of galaxies and clusters, through billions of years of expansion and cooling, and yet they still reach us tiny survivors of an age when light itself was new. Every time an astronomer captures one, it is as if a message from those first stars has been opened at last, its ancient script decoded by minds that evolved in the very structures those stars helped to create. The echoes in the infrared remind us that the universe is not silent, it hums with memory. Even as galaxies grow old and stars burn out, the faint background of annihilation-born light persists, undiminished by distance or time. It is the most enduring legacy of the cosmic dawn, a soft, omnipresent murmur woven through space. When we look into that deep red haze, we are not merely seeing the past, we are listening to the first whispers of existence itself, the sound of the cosmos learning to shine. Every story of creation carries within it the seed of an ending, and the first stars were no exception. Their light, though ancient, was never meant to last forever. The universe they illuminated was young and restless, expanding and cooling, reshaping itself with every passing epoch. The dark stars that once glowed with the quiet warmth of annihilation began, one by one, to fade as their dark matter fuel ran out. Their balance, so delicately maintained between gravity's pull and annihilation's heat, finally broke. The gas that had been held aloft for millions of years began to collapse inward, its own weight sealing its fate. What followed was an ending both silent and absolute. Without sufficient heating to counter gravity, each dark star contracted swiftly, its core growing hotter until fusion tried to ignite, but it was too late. The immense mass, far beyond the limit of stability, could not be supported. Gravity overwhelmed every force, and in a final act of inevitability, the star fell into itself. There was no explosion, no dazzling supernova to mark its death. Instead, the universe gained something darker and more enduring, a black hole. This quiet end, repeated across countless halos, transformed the structure of the cosmos. Each collapse seeded a gravitational well where none had existed before, pulling in gas, dust, and radiation. These wells became the first true centres of organisation, the nuclei around which the first galaxies would form. In their depths, the dark stars shaped the blueprint for everything that followed. Their final light, stretched across eons, now reaches us as the faintest whisper in the infrared, the last remnants of their annihilation-born glow. The fusion-born giants of the same era met a different fate. Their lives were briefer, their deaths spectacular. When they exhausted their fuel, they detonated as titanic supernovae, releasing floods of heavy elements into space carbon, oxygen, silicon, and iron. Those elements became the seeds of chemistry, the foundations of planets and life. Yet their light, though brighter, was less enduring than that of the dark stars. The supernovae burned fast and fierce, their brilliance fading within months. In contrast, the red glow of annihilation had lingered for millions of years, suffusing the early universe with a steady warmth. Together, these two kinds of stars completed the first great cycle of cosmic evolution: creation, transformation, and return. The last light of the first stars marks a turning point in cosmic history. It represents the moment when the universe shifted from primordial simplicity to structured complexity. The dark stars, in dying, handed the torch to their descendants, the black holes and galaxies that would dominate the next phase of cosmic growth. The heavy elements forged in the fusion giants spread outward, enriching the interstellar medium. From that enriched gas, new generations of smaller, longer-lived stars were born. The universe was learning to recycle itself. What had begun as a single experiment in illumination became a self-sustaining process. The cosmos had discovered permanence. To see the last light of those first stars is to glimpse the end of innocence. Their radiance was the universe's first act of artistry, pure and unrefined, untouched by the complexity that would follow. When it faded, the universe entered its adolescence, messier, denser, and filled with the chaotic interplay of forces that would shape galaxies and clusters. Yet something of that first light remains woven into the structure of existence. The photons emitted by dark stars more than 13 billion years ago still drift through space today, passing unnoticed through our solar system, through our atmosphere, even through our bodies. Every moment we are bathed in the faint relic light of a vanished age. It is too weak for our eyes to see, too cold for our skin to feel, but it is there, a quiet reminder that everything luminous in the universe was born from darkness. There is a melancholy beauty in that idea. The first light was not a dawn that lasted, but a spark that gave way to deeper forms of order. The dark stars did not survive into the present, yet their absence is itself a kind of legacy. They left behind not ruins, but frameworks, galaxies, black holes, and the subtle traces of annihilation woven into cosmic radiation. Even now, their story continues in the patterns of light we study, in the invisible scaffolding of dark matter that still guides the motion of stars. To study the last light of the first stars is to read the closing line of the universe's first chapter. It is the moment where mystery becomes memory, where the act of creation gives way to reflection. The dark stars may be gone, but they are not forgotten. Their final glow still threads through space, faint yet unbroken, the lingering breath of the cosmos's first attempt at brilliance. The story of the dark stars is, at its heart, the story of the universe learning to turn shadow into substance. Though their light has long since faded, their influence remains etched into the very geometry of the cosmos. Every galaxy, every cluster, every filament of the great cosmic web owes part of its existence to those first invisible architects. They were the bridge between the primordial simplicity that followed the Big Bang and the structured complexity we inhabit today. In their rise and fall, they demonstrated one of the universe's most profound truths, that creation often begins not with light, but with the unseen forces that give light a place to shine. The legacy of darkness is not merely a poetic metaphor, it is a physical reality woven into the foundation of existence. The dark matter that once powered those titanic stars still dominates the mass of the cosmos, shaping its evolution silently and persistently. It forms halos around galaxies, binds clusters together, and sculpts the filaments of intergalactic space. Without it, galaxies would scatter, and the night sky would dissolve into chaos. The same invisible substance that once ignited the first light continues to govern the motion of everything that shines. In this way, darkness is not the opposite of illumination, but its framework, its eternal partner. The legacy of the dark stars also lives on in the black holes they left behind. These remnants, the collapsed hearts of once luminous titans, became the gravitational centers around which the first galaxies coalesced. Over billions of years, they grew into the supermassive black holes that now lie at the cores of galaxies like the Milky Way. Every quasar that blazes in the deep sky is a direct descendant of those early collapses, a monument to the dark star's final transformation. Through their deaths, they ensured that the universe would never again be formless. The galaxies we see today are the matured descendants of that first generation of order sculpted by gravity, illuminated by fusion, and framed by dark matter's invisible pull. Even the concept of cosmic evolution takes on new meaning when seen through the lens of this legacy. The dark stars were the universe's first feedback mechanism. Annihilation, heating delayed ordinary star formation, giving the cosmos time to grow large enough to sustain complexity. Without that delay, the early universe might have burned too quickly, producing stars too soon and too small, exhausting its gas before galaxies could form. By slowing time, the dark stars made future creation possible. Their restraint was as essential as their radiance. The irony of their name, dark, is therefore almost comical. They were among the most luminous objects to ever exist, yet they owe their existence entirely to what cannot be seen. Their lives remind us that visibility is not the same as importance, that what glows brightest often depends on what remains hidden. Just as dark matter gives structure to the universe, unseen forces, ideas, energy, time shape all things that emerge into the light. The dark stars were, in a sense, the universe's first teachers, showing that even destruction can sustain creation, that even annihilation can give rise to beauty. Humanity's attempts to understand them are part of that same cosmic story. When we point telescopes like Webb into the abyss, we are not merely looking backward in time, we are tracing our own lineage. The iron in our blood, the calcium in our bones, the gold in our rings, all exist because the universe once contained both fusion-born and annihilation-born stars. The balance between those two types of creation, visible and invisible, fleeting and eternal, is the balance that made life possible. We are quite literally the legacy of darkness made conscious. As science pushes further, the mystery of dark matter remains unresolved, but perhaps it no longer needs to be feared as something alien. Instead, it can be seen as the universe's oldest companion, the silent counterpart to light. We may never see dark matter directly, yet we see its work everywhere, in the motion of galaxies, in the bending of light, in the steady expansion of cosmic structure. The legacy of the dark stars ensures that even if the universe one day grows cold and dark again, its memory will persist in the geometry they helped define. Their lesson endures, that every illumination, however brief, leaves a mark that cannot be erased. To understand the cosmos is to understand that light and darkness are not opposites, but phases of the same eternal process. The universe was born in shadow, learned to shine, and will one day fade back into the quiet that birthed it. But the patterns it created of gravity, of order, of possibility will remain. The dark stars may have been the first to reveal this truth, glowing softly in the depths of nothingness, reminding creation that even in absence there is power, and even in the darkest silence there waits the potential to begin again.